Hello friends, welcome back to my YouTube channel Infinite Knowledge, and I am back with one another MATLAB simulation based project. So as you are aware about that, I have already uploaded one video regarding to the power factor correction method. So yes, you can see that video over my YouTube channel. This one, the automatic power factor correction, and the simulation for that model is this one. So as you can see in this model, as you turn on this load, according to that load requirement, your capacitor banks, these are capacitor banks which turn on by this switch itself. So there is no any actual control, there is no any active power based control. So how you can implement that? What is the automatic power factor controller, and by using this triac, how you can control the switching? These are the PWM block that used to turn on and off your switching device, and these are some Thyristor. So it is a Thyristor based power factor controller, and how it is work we will check it soon. So why we have implemented this model, why we have updated the older model with this one? Because here you can turn on and turn off your load no matter what is the load. According to your load, according the change in the load, this power factor controller, the MATLAB function block model will generate the firing angle, and that firing angle will use to trigger this PWM. This is a pulse generator, and according to that firing angle, this capacitor bank will come into the picture, and whatever the power factor is required, that much amount of power factor or that much amount of reactive power will feed to the circuit, and not the total load. So you can see here, whenever I turn on, this is the previous model, and whenever I just turn on this switch after some time delay, by this time delay, this totally block will come into the picture whenever I turn on this load. So here you can see these loads are fixed. I have considered the load in the 4 step, 1 2 3 4, and according to the load I have designed some fixed capacitor, and this fixed capacitor will come to the picture whenever I turn on this switch. But if you comprehensively go through this model, you can see that there is the two switches, but no matter what is the load, according to this is the some time delay which I have required to turn on and off frequently. So if I did not use this delay block, it will continuously on and off, so that may cause the unnecessary switching. So this is the you can see this is the firing angle control. This is thyristor based control, and how this thyristor based control is working, that based example is from this block. So you can see here, this is a three-phase sine wave or three-phase 415-volt power supply, and yes, you can see why it is red, because I have considered variable D. What is the variable D? If I double click over this function pulse generator, you can see this is a variable D has designed. D means our firing angle. So how you can set? You need to set some value of D. So I am consider D is equal to 0 right now. Okay. So if I consider the D is equal to 0 and refresh this model, you can see fix. Okay, so refresh is done and D is assigned for this block. So forget about this control, above control, and just focus over here. So whenever I start the simulation, you can see that, okay, just wait until it gets started. As you can see here, the simulation is started and our angle, firing angle D is equal to 0. So if I stop the simulation after some time, you can see this is the supply that we have fed to our resistive load. Here I have considered the resistive load for a better clarification. Okay, so if I check the voltage and current, you can see pure sine wave is applied. This is just initial condition, but you can see pure sine wave with all, there is no any control. Why there is no any control? Because D is equal to 90 degree, D is equal to 0 degree, sorry. Now if I D is equal to 90 degree, I change the model, you can see the D value is changed over here, and again check the simulation, what is the waveform that we are getting and what is the output. So once the simulation is start, I just stop after some time. Okay, right now simulation is stopped, and if you again go through the block, you can see only the 90 degree the firing angle is set to the 90 degrees. So initial 90 degrees is obsoleted, and this is how we can control the voltage over our load. And by this, two anti-parallel thyristor, which is work as a triac. So this is the logic that I have implemented over here to take picture the capacitor bank. So this is how it is working, and the firing angle is set by our logical controller MATLAB function, and that PID base. So this is how the system is working. This is why I was explaining this triac system or this system initially, and there is a resistive load. That's why there is no any delay in between voltage and current. Again, I set to D is equal to 120 degrees. So as I increase the firing angle, your output is reduced, because if you consider a simple sine wave, if you consider a simple sine wave, if you simple consider a sine waveform, okay, yes, yes, this is the waveform. So initially we have considered d is equal to 0. That's why we are getting the pure sine wave. At then we have considered 90 degrees of firing angle over here, and we are getting this waveform only. Similarly, here only this waveform 270 to 360. And right now I have considered a 120. Okay, and simulation is done. I have said in d is equal to 120 over here. Okay, so what is the waveform that you are getting? So if I zoom in, if I clearly zoom in, okay, you can see 120. 120 means only this part is there, only 120, and only this part 300 to 360. So this part is 120 to 180, and this part is 300 to 360. This is how you can control your voltage. So if you further increase the delay, d is equal to, if it is 180, if I consider a 180, what we are getting, I don't know, I need to simulate it. So it is a 120. I think we are getting 0 as a output because we are firing at a 0. So yes, you can see there is 0, very low, nothing we are getting over there, because we are firing over here, we are firing over 0. So 0 means you are getting nothing. But if you consider a 150, if you consider d is equal to 150, then you can get something in the output. So 150 is this much, 150 to 180, 330 to 360. So this is how you can control the supply to your system. Okay, so this is what you are getting. So as you are changing the value of d, your pulse width will change. So again I set to a 30 degree. It means that your waveform width will increase, and now you are firing over 30 degree, means here this is the waveform that you are getting from 30 to 180. If you want to check, you can check over here. You can see 30 to 180, 30 degree firing angle. If you consider one waveform, only one, this one, so 30 degrees firing angle, then again at the negative cycle you are getting 210, because this 30 degree is not considered. So this is how you can control the supply to your load. This is a resistive load, that's why you are getting pure sine wave. But here is not a resistive load, it is the resistance plus capacitance, whereas the capacitor value is very high compared to the resistor. Resistor is the simple internal resistance of the capacitor. So at now, whenever I try to simulate the circuit, initially I consider both the load is with the off condition. So whatever the power factor was initially considered, you are getting the output. So again I try to run this simulation and explain you how this firing angle is changed according to our load, and it will help us to use only a one capacitor bank, whereas initial waveform, if you consider this, there is all the separate capacitor bank for separate loading condition. But here the advantage is that you need to use only one capacitor bank, which is some higher capacity, which is the capacity to improve the power factor for both the load. So if I consider both the load, and if I consider a 15 kVAr capacitor for both the load, for total load, then have to use only a 15 kVr capacitor. Whereas initially what we are getting, if this is the load which required a 15 kVr capacitor, that I have used, this is a 15 kVr capacitor. And then if this load required a 10 kVr capacitor, then I have used a 10 kVr capacitor separately. Here we can not do that way, and we use one total capacitor. Whatever the load is changed according to the power factor angle, which is real-time monitoring, which control the firing angle of this system. And as you are aware about it, how the firing angle affect our uh, system. So yes, now I start the simulation and explain you how this simulation is working. So this is the upgraded model of the previous one. So as you can see, I start the simulation. Initially both the load is in the off condition. So the whatever the by default value are coming, this is a 0.8871, but there is no current in the system. And as I start the simulation, I add the load. You can see your power factor is nearly 0.94. Your power factor must be greater than 0.9. So you are getting this power factor, and you can see the angle is 0. So it means totally all the this angle is controlled over through here. This is the firing angle. You can control the firing angle by this manual switch also, and you can see this is a 0 degree. But as as you are aware about, initially if I consider d is equal to 0, you will get a pure sine wave over here. But here it is not happening because the resistance and capacitive load is there. So for d is equal to 0, if you comprehensively note that, so initially there is no load, that's why you are getting pure sine wave. But as it's come to the picture, this is the reactive power is fed by, why it is like a waveform, because capacitive load is there, and this is a spike. This is what you can say, this is the reactive power fed to your system, and it's improved the power factor. The real time power factor is improved. And if you check the P and Q, you can see that how P reactive power is reduced. Your initially your power your spikes is high. Why it is a spiking waveform? Because we have used a Thyristor, that's why you are getting some spike. But as it's come to the picture, your reactive power is reduced. This reactive power is reduced. Okay, so this is the condition at which your capacitor fed power. This capacitor come to picture and fed reactive power to your load, and which improve our power factor indirectly. So here how we are measuring the power factor, this is very basic formula. I have used instantaneous power, then this is a formula U square V square. So if you are aware about this formula, power factor is P. P means active power, S P square plus Q square, these two. This is our power factor, this formula I have used. And to get power factor, then I have get some proper value that is fed to this function block, MATLAB function, which continuously sends the power factor and give us some output. So if you can see, it is not just a fixed value, you can see it is a step by step. So it sends the value, and in 5 steps. Initially it is a 45 degree, then 40 degree, then 35 degree, then 30. So it's checked for each and every degree, and if in between your power factor is set, if your power factor is greater than 0.9 for 25 degree, then it will stuck to the 25 degree. So it is a real time monitoring, and maximum and minimum value is defined over there, then 0 degree and 120 degree. So as I again start the simulation, so initially it was a 45 degree by default, and then it is changed to the as per requirement. As you can see, angle is decreased by, because we are not getting power factor to our required value. Okay, then it's set to the 10, because we get our value at a, we get 0.9 greater than 0.9 at a 10 degree. So it is stuck to the 10 degree and did not reduce to the 0. Okay, now you are getting the continue. Now if I increase the load, you can see it is unable, it is able to maintain the power factor greater than 0.9, then it's not matter. But if I reduce this much load, then what happen? Okay, then also the power factor is maintained, and it's try to maintain over whatever the requirement. So I stop the simulation once again, and once again I start the simulation for this load is in the picture. As you can see, initially the 45 degrees there, but power factor is not maintained. As power factor is not maintained, the angle is reduced. Angle is reduced means more power is fed by this As the angle is lower, you are getting pure sine wave. As the angle is reduced, you are getting more output. As the angle is reduced, as the angle is increased, you are getting less output. That's why I have used this concept over here. And for this we are getting 10 degree. If I reduce it, it's below the power factor, that's why it come to the zero condition finally. Okay, so I need to restart the simulation once. I again started the simulation and checking that randomly power factor is less than 0.9. Initially it is a 45 and it has reduced back because there is no current in the system, because there is no load. Both the load are in the off condition. As I started this load, you can see my power factor is 0.467 by 0 degree. As I increase this, my power factor is greater than, it's go to the greater than point. So at 5 degree we are getting power factor greater than 0.93. So it is a real time simulation and the calculation is backend. Calculation is there in the backend by this MATLAB function. You will get the code of MATLAB function in my description box and you will get this file and the calculation for the kVAR requirement according to the load for both the files. So you will get this both the file, active power factor and the normal power factor method. This is the conventional method and this is the advanced method in which we are using this firing angle control and to get the real time power factor change. So yes, initially I have told that this is the slider switch. What is the use of this slider switch? I wanted to explain that as I start the simulation, by default you are getting some values, your firing angle value. It's by default is a 10 or 5 according to our requirement. So it is a 10. But if I change the firing angle, so yes, you can see this is a 10. Is I increase the firing angle, as you can see I increase the firing angle to 45 or 50, 56. I think so. It is a sorry, 51. So if the firing angle is increased, then obviously your power factor will reduce. You can see your power factor is reduced and it cannot maintain the power factor. Why it is happening? You can see initially your system is feeding some load, feeding some reactive power to your load. But what I had done, I had reduced the angle. So if you this pulse width is reduced, that's why it's unable to feed the sufficient amount of power to your load. So again what I am doing, I randomly increase this value and we'll check. So again you can see there it's 90, it's 51, and at 51 we are getting, what is the power factor that we are getting over here? It cannot maintain, both the load is on condition, even though we are getting only a 0.637 power factor, which is very lower. And if I reduce or increase the angle again, if I increase the angle again, it's increased to like a 100 degree, then you can see the waveform. You can see it is reduced and after some time it's totally zero. There is no, it it is it what it means that this is a nearly zero. It's mean that you are not feeding any amount of power to your load. So that's why your power factor is again reduced to 0.5. So what I am doing, I just not changing anything in the slider. I have used slider to just explain you very well about the firing angle. So yes, you can see here it is again 104. Firing angle is 104 and we are getting power factor is a 0.59 or zero point 0.6 nearly, which is totally inefficient. So what I am doing, I just reduce the power factor or angle to minimal, like a 3 degree or nearly zero, which is. So initially your power factor was 0.59, it's increased to 0.94, which is actually required. So this is how firing angle affect your power factor. And if you wanted to check how the waveforms are affected, you can check that initially your power factor was the angle was 100 degree, that's why you are getting 0, but as it is reduced to 3 degree, it's your capacitor come to picture and feeding sufficient amount of reactive power to your load to maintain the power factor. This is how this this system, this firing angle is working, and this is how Thyristor based system is working to maintain your power factor in real time. So thanks for watching this video. If you have still any query, just comment it. I will definitely reply. You will get this file in description box, the code of this file in the description box, and you will get this file also, and the what is the calculation for the load as well as the capacitor bank, that is also handwritten calculation. You will get all the data in the description box. You can connect with my email id that is given in the description. If you have any query, you can just comment. If you want any type of MATLAB project that I work, that if you want that I working with you and work on your project by your demand, then also you can connect with me through my email id that is given in the description box. Thank you very much. Thank you for watching this video.